Hello, this is the third part of our tutorial on BERT classifier fine-tuning with PyTorch, HuggingFace and Catalyst. So for now we covered data preparation, and now we're going to discuss the model, so how we fine-tune the model, so how it looks like, and well, whether we need to customize a bit the code defining our model. And then we're going to discuss training the model with Catalyst in the fourth and the last part of this tutorial. So last time we covered the part from reading files, reading data frames from CSV files through PyTorch datasets to data loaders. Last thing before we switch to the model itself, I wanted to stress again this Wordpiece tokenization. So we covered an example, something like I enjoy playing football under rain, and then how DistilBERT tokenizer processes it. So we covered everything, well, not everything, but how it looks like, how the input to the model would look like. I would only like to provide one more example, because this example with I enjoy playing football under rain, it's not perfect in the sense that it does not show the full power of a Wordpiece tokenization. Let's show a bit more dirty example. So I'll just comment this out and create a new string, also called input text. Let's write something dirtier, something like yo dude, I'm Timothy from Russia. Well, maybe we can have some typos, something like that. So let's see how BERT would process this string now. And I will only zoom in just a bit so that you can see the code better. And so that my face does not cover too much. Okay, looks good. Right, okay, so now we have a bit more dirtier text, and let's see what BERT would do with that. Okay, and now we see that, now we see Wordpiece tokenization in action. So it does not know the word yo dude, so that's why it split it into yo, and then these two parts, so these are word pieces. So these two parts are there in the dictionary. So this part starting with two special symbols mean that it's a continuation of a word. So it's not a word du by itself, it's just a word piece. So it started with something and then we had du. So that meaning that it's part of word. And the same for this de, and the same for it split the name Timothy into three word pieces. And you see it somehow handled typo in word Russia. Yeah, and we can simply check it. So we had our vocabulary, and we can check whether it has some specific token or not. So obviously it does not have the word yo dude, so it does not return anything, meaning there is no such word, but it does have yo. It has some ID in vocabulary for that. Okay, so you can read more about Wordpiece tokenization, and I will clean up this notebook and I will leave some links to Wordpiece tokenization so you can dive into how it actually works. Right, okay. So now let's switch to the model. So it's we could have simply imported BERT for sequence classification from HuggingFace, but I deliberately defined it here so that we can go through the code and understand it a bit better. And then we'll go to HuggingFace source code and we'll examine a similar implementation, and we'll see that it's not really intimidating to dive into source code just a bit. Right, so we import Torch, and it's a submodule NN, neural networks. And then from transformers, we'll import autoconfig and automodel to load model weights. Okay, now we have a class defining, so that will actually be our BERT, or well, a bit lighter DistilBERT model performing sequence classification. well, text is a sequence, so yeah, we'll be fine-tuning precisely this model. So it actually needs to have a constructor and then a forward method. And so remember, all the power of deep learning is that it can do a backward step for you automatically. So we need to define a forward step. But first of all, let's look into constructor. So constructor takes 3 arguments in this case. It's a pre-trained model name. Again, in our case, it will be DistilBERT base uncased. And then to perform sequence classification, we need to know the number of classes. And it's a tradition, a good practice. So before the final linear layer, we'll add dropout, and so we'll have this dropout rate as a hyperparameter as well. So we'll load configs. So yeah, we'll now see how precisely it looks. But just going through the code, we see that we'll load configs for the model. Then we'll load the model itself with this config file. And then the final layer will be a linear layer mapping from some hidden size to our number of classes, so 5 in this case. And so the forward method, something is going on here, so this we'll cover in detail. So we'll take some embeddings from our BERT model, and then we'll do something on top of that. Okay, so let's reproduce these steps. So we need to load the model and configs, and we'll see what exactly this model is. Right, so our pre-trained model name is DistilBERT base uncased. We saved it earlier. And now we'll have 5 classes, and then we'll define a model. So the model can be automatically downloaded with this pre-trained model name. So here, I think I downloaded it earlier, but here it can take some time. So typically you need internet connection to load weights from the internet. So if we change it to something more, to a larger model, let's say just BERT based in case of BERT large, it will start downloading weights. Right, so let's take a look at the config. Okay, it says that it's the architecture, the underlying architecture is DistilBERT for masked language modeling. Do we have something interesting here? Well, we see that it maps labels to some strings and the same back. Okay, we see that it has 6 transformer layers and 12 heads. It has some dropouts, vocabulary size, as we've seen, it's 30,000. And hidden dimension is 768. It's the dimensions of internal vector representations. Well, at this point, it's good to study some JLMR's post to have idea of this architecture, and we can simply print it by just running model. And now it says that it's a DistilBERT model. We see that it has some embeddings first. So it creates word embeddings, and you see our vocabulary size 30,000, and this dimension 768 is dimensionality of each embedding. So both word embeddings, so position embeddings, and then it will be everything, all internal representation will have this dimensionality. Okay, so it has word embeddings, then position embeddings, and further we see that it has 6 transformer blocks. So here goes transformer, we see transformer block number 0. If we just scroll down, we'll see that in the end it has transformer block number 5. So in total 6 transformer blocks, and each one of them consists of a multi-head self-attention, and it's here I link to JLMR or Chris McCormick to dive into this architecture. So 2 components, multi-head self-attention, and then feed-forward network on top of that, with further some layer norm. And we see this part repeats 6 times. Okay, we have our model, so let's understand how it works. create some space here. So we see that further in our forward method, we use this self.model. So we run our example through this model. So let's understand how this part actually works. Right, so before that we created our Minibatch. So let's basically just scroll up and see that we had data loaders, and then we had a Minibatch, and yeah, let's just print again how it looks like. Yeah, so Minibatch, it has tensors for input features, then a tensor for attention mask, and also a tensor for our targets that we are going to predict. Right, so let's understand how this model works. So first of all, it's good to call documentation on that. So if you just run model and then pass some arguments, internally it runs forward by default. So let's see what forward method takes. And we see that it needs input IDs, then an attention mask. You can also mask some heads, so maybe you don't want to use all of the heads. You can mask some of them, and some other arguments. Well, we can read thoroughly this document string, but at least we need some input IDs. And well, if we prepared an attention mask, let's pass attention mask as well. All right, so we need to pass input IDs. So we take them from our Minibatch, and yeah, it's a dictionary, and it has the keys, the key features. Let's just print, sorry, Minibatch and keys. Right, so we have features, which are our input IDs, attention mask, and targets. So let's just pass our features here as input IDs, and then we have an attention mask. So the same. From Minibatch we take the attention mask, and we'll ignore the head mask. So we'll just use all the heads to process this particular input. Okay, so we do have something. We can just print it, or we can just check its type. Okay, we see it's a tuple. Then we can check its length. A tuple of length 1, so we can safely take the 0th element. Okay, let's now print it. So we see that now that it's a tensor. Let's print its size. Okay, it's a tensor sized 2 by 16 by 768. What it stands for, actually, it's the first, so the 0th dimension is our Minibatch size. So we defined batch size of just 2. 16 is the sequence length. So in a more realistic scenario, this will be 512. And 768 is our dimensionality of internal representations. And so now if we go to JLMR's post, or even maybe to my previous presentation, so if we just take a look at schematic representation of BERT architecture, so the output will be, remember the 0th dimension is batch size. So for each example, we'll have representation, so this vector for each of the tokens. Yeah, let's just compare it again. So batch size, sequence length, and then dimension. So for each example and for each token, so here we see these green tokens. So in our small example, 16 of them, but in a realistic example, there will be 512. And we start with a special CLS token and end up, well, it's not written here, but we end up with a separator token. And so for each one of them, we'll have a vector sized, 768. And so this all packs into a 3-dimensional tensor of these sizes. Right, so just schematically, I'll denote dimensions as batch size by sequence length and by these embeddings dimensionality. Okay, and now we can play around a bit with the forward method again. So for this distal BERT model, We see there are some more flags, so we can, if we need to, we can output attentions and analyze them, and we can output hidden states, and well, we can also return output in a bit different form, in the form of a dictionary. Yeah, let's take a look at output hidden states. Okay, let's take a look at these two params. Output hidden states. Let's just add these two. Right. So we'll just say that we also would like to output hidden states. Sorry. Output hidden states. We'll just set it to true. And return dict, we'll set this as true as well. Right, and now, okay, let's call it BERT output 2. Right, so now we see that BERT output 2 will be, yes, special object base model output, which is basically just very similar to dictionaries. So it has keys, and now we see that we have two keys, last hidden state and all hidden states. So last hidden states is exactly the same as we had here. So by default it returns last hidden states. So let's just take a look. Yeah, it's a tensor, and let's check its size. And again, it's 2 by 16 by 768. So this is our last hidden state. And in that picture, it's yeah, here on top we have a last hidden state, but here in this blue rectangle or black box we have all these intermediate hidden states, and we can actually take representations from there as well, and they sit here in hidden states. So if we take a look at BERT output 2 hidden states, now it's actually a tuple. Let's check its length. Okay, length 7. So yeah, so this is, remember we had 6 transformer blocks. So we have outputs from all of them and plus our last hidden state. Yeah, so we can take a look at the 0th element here, and we see that it's PyTorch tensor. We can check its size. And again, it's 2 by 16 by 768. And actually, all of them have this dimensionality, so we can take internal representation from each of transformer blocks. Yeah, let's just make sure that the last one is the same as our last hidden state. Let's just check these. Right. Okay. Yeah, I think PyTorch has something like equals, if I remember correctly. No, it does not. Okay, but we see that yeah, these are, yeah, these tensors are actually equal, and so we so the final tensor here in hidden states is actually this last hidden state. Well, so this can be actually useful. So all these transformer blocks, they capture a bit different information. So maybe for a simple task like text classification, we don't need that. But for more involved tasks like co-reference resolution or maybe part of speech tagging, it's they perform research on that, and they see that different heads capture different information. So typically on some lower heads you have some specific some general text features, and closer to the top, so closer to the last hidden state, you have something more specific to your classification task at hand. So it's very similar to features in different layers in a convolutional neural net, where you have general visual features like all these small strokes and punctures, and then closer to the end of your network you have more domain-specific, more fine-tuned features. So you might want to use not only your last hidden state, but also some intermediate hidden states as well. Right, and so let's now analyze how this classification top looks like. So what we're doing here, let's just copy all of that and then yeah, analyze it in more detail. Right, so we took BERT output, and remember it was a tuple, and so by default it's just, as we did initially, it just outputs last hidden state. So here a sequence output is the 0th element, meaning that it's precisely this last hidden state. Okay. And then what we do further, we yeah, let's just there's some hotkeys to split Jupyter cell, but okay, I'll just comment it out. So now we have sequence output. Yeah, it's as we've just seen, it's 2 by 16 by 768. Yeah, so batch size by sequence length by dimension of our vectors. And then what we do further to do classification. So we'll perform some averaging. So we'll average embeddings of all the tokens. So yeah, going back to this picture, so we'll average embeddings for all of these green tokens. So this will serve as our sentence representation. There are actually alternatives to that. You can take an embedding from this CLS token, which also serves as some general sentence representation, and you can experiment what works better. So there's some evidence that averaging token embeddings works just a bit better. But you can experiment with that on your particular task. Or you can just take, if we here from sequence output, we can take the 0th element. Well, if we take sequence output, yeah, everything for our, so all our examples, and then in the first dimension, if we take number 0, so this will be our sequence token representations, right? So these, sorry, not sequence tokens. So these are representations from the CLS token. So you might want to take these and then concatenate these with averaged token representation. So this is just an alternative to take embeddings from the first CLS token. But what we are doing actually here, this pooled output, it's averaging all token embeddings. So this axis number 1 means that we average everything across this sequence length. So for all of our tokens, we average these representations, and so this is now of size, batch size by dimensionality. So in our case 2 by 768. And then further we do I would say traditional things. We add dropout, and then we add a classifier on top. Right, so dropout does not change much actually. Well, it does not change dimensions, I mean, but let's reproduce this step as well. So we are adding a dropout layer. Okay. So we had the dropout rate 0.3, and a classifier on top will map from this hidden size 768 to our number of classes, which is 5. Right, so okay, so then then we'll transform our pooled output, adding dropout, and then the final scores will be classifier applied to this tensor. Well, maybe it's a bit better to rename this variable so that we don't confuse this pooled output with this one. But okay, so what we have here is the final scores tensor. Yeah, it's 2 by 5, right? So our number of examples the batch size by the number of classes. And if we just print it, it's these are scores. So yeah, this can be some either positive or negative numbers. So we don't necessarily apply here some activation like softmax or sigmoid. Well, for multi-class classification, we'll do a softmax, but our model would just return raw scores. We can always take argmax to identify the predicted class. No problem with that. Oh, right. So now let's take a look at the our class definition again. So I'm saying here that it's a simplified version of the same class by HuggingFace, and we can go and actually analyze source code, which we'll do in a minute. And let's just take a look again. So we had in our constructor, we defined the model, the classifier on top, and then dropout layer. And then here we take the output from the model, from DistillBERT model in this case. So it serves as a representation of our text sequence, basically a sentence. And then we take here the final layer representation, and then apply averaging for all tokens, and then adding dropout and linear layer, and return scores. So yeah, batch size by the number of classes. Okay, so actually, yeah, analyzing the source code of a similar class from HuggingFace, it's not too intimidating. So we can go just to HuggingFace transformers, to the GitHub repo. So here we can navigate to source itself, so src/transformers, and then yeah, they changed it just a bit, then further to models, and yeah, we need DistillBERT. Yeah, we see that we have configuration, modeling, and tokenization. So let's take a look at the model. Right, well, of course, it's a pretty large file, but we can search for what we need. So if we just search for DistillBERT 4, we see that it has different applications. Yeah, so we can do just masked language modeling with DistillBERT, and we have a separate class for that, which inherits from DistillBERT pre-trained model. So yeah, we can do masked language modeling with that. So just providing some blah 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 mask token and then something else, and it will try to fill this special mask token with something else. We have DistillBERT for sequence classification. Yeah, that's precisely what we need. But let's just take a look at the other applications. DistillBERT for question answering. DistillBERT for token classification. Yeah, here it goes, named entity recognition or part of speech tagging. DistillBERT for multiple choice. Yeah, I'm not familiar with this application, but it's looks like question answering with multiple choices. Yeah, and that's it. So you see it's actually here in code we see this idea that we have a single encoder. So BERT, or DistillBERT in this case, serves as an encoder, and then we have all the different applications with all the different decoders, and further all the different use cases for this model. So we see it in code, at least by the fact that all these classes inherit from DistillBERT pre-trained model. Right, so let's hop to DistillBERT for sequence classification, and we see that it's pretty similar to what we've seen right now. So we have a number of labels, we have this underlying DistillBERT model, and then the output is just a bit more involved. So we have one more layer pre-classifier. We see it's square layer. So this number of dimensions by the number of dimensions. So this 7, that would be 768 by 768, and then a classifier and dropout as we've seen. And essentially the forward method is doing what similar things what we've seen right now, right? So we have all these hyperparameters, sorry, just parameters, all these arguments. So we pass input IDs, attention mask. We can mask some of the heads, input embeddings. I think we can provide some learned input embeddings. Okay, not sure about this argument. We can provide labels as well, and the forward method can return losses, and it can output tensions, it can output hidden states, and it can output it all as a dictionary. And so we are taking output from the DistillBERT model exactly as we've seen right now. So this is the encoder part, and then we are taking hidden states, so the 0th argument, batch size by sequence length by dimensions. So then here the pulled output, you see it here we take representation from a CLS token. So this number, so this 0 means that yeah, from all the token representation, we take only the 0th one, which is CLS token. And further, they add pre-classifier here. So this is a squared, well, I call it a squared matrix, meaning that dimensions are, yeah, in this case 768 by 768. And then they further apply ReLU, so non-linearity, then dropout, and then classifier. So you see here their classification head on top is a bit more involved. And so essentially they call it pooling. So taking CLS token representation and then this operation of pooling and then classifier on top. And further, this forward method can also return loss. So if labels are provided, then we further have a choice whether we are solving a regression task or a classification task. So we can return either MSE loss for regression or cross-entropy loss for classification. So you see, yeah, so number of labels equals 1 would mean that it's a regression, and something more greater than 1 would mean classification. And then, yeah, if we didn't pass return dictionary, we output just a tuple. So yeah, logits would be the scores, and then yeah, everything else. And we can also return loss function. Well, and if the return dict parameter is passed, yeah, then the output is some special class implementation, which, well, basically inherited from a dictionary. But we output this in a more disciplined way. So it would have keys, loss, logits, hidden states, and attentions. And we took a look at into these hidden states key. Right, okay, so you see that it's, well, I wouldn't say that it's easy to analyze source code, but once you get accustomed to that, it's not really very hard, not too intimidating to analyze source code. And now we see that indeed our implementation is a bit simplified implementation of this class DistilBERT for sequence classifier. Right, and I can actually update the link here. Right. Yeah, so it was SRC, transformers, models, DistilBERT, and then, okay, it's not as simple as that right now, so the path just a bit changed. Right, okay, so now we are familiar what the model is, how it works, and further we can proceed to training. And so here we'll use Catalyst. So the final fourth part of our tutorial is gonna cover training and then evaluating predictions.